project, we'll be talking about cell phone antennas. The class we're taking is 2FH3 group project, and our group number is B21. The following members are listed below. Let's go on to the agenda for today. The topics for today we will be covering. We're going to go over some introduction to antennas. We're going to go over what primary cellular antenna does, transmits and receives, some facts and terms about cellular antennas, what's SAR, what's TRP. We're going to go over some frequency ranges, GSM, 2G, 3G, 4G. I'm sure everyone's familiar. We're going to go over some dipole antennas, what that means, efficiency, what that means, bandwidth, impedance matching, and some designs, why the location of antenna is where it is, and number 6, our final topic, will be on simulations that we've done over 4NF antenna.
So I'm going to be covering the introduction to cellular antennas. So what is a cellular antenna? It's pretty much just an electrical device which converts electrical power into waves. So how does it work? Well, it uses an oscillating current to produce electromagnetic waves, and another antenna would communicate with this antenna by intercepting some of the power produced by the electromagnetic wave in order to produce some sort of recognizable voltage. So why would I care about this? Well, every cell phone, that smartphone or old phone with like the gigantic antenna on the externally, they all have antennas. So pretty much big things come in small packages. So everything, like I said in the last slide, every single cell phone has some sort of cellular antenna. So there are many different properties and often more than 1, 2, or 3 antennas in each phone. So the primary antenna is for primary communication, so like talking and things like that, hence the word primary. And it's the only antenna that transmits. There's also a diversity antenna which receives information, a GPS, Wi-Fi, and NFC antennas for communication with satellites, like a GPS, for routers, for Wi-Fi, and for other devices like Bluetooth with NFC. So these antennas aren't as simple as a normal radio antenna. So they have various requirements, like Rogers would need a different antenna for one phone, where Bell would need a different one, and Wind would need a different one. So they also have a bunch of regulatory requirements where the federal agencies need privacy settings and public safety, so to keep the public safety all in check. So what's the difference between a normal radio antenna you see with the radio towers emitting and a cellular antenna? So back in the day, there was only about 1 radio tower per town, and each tower only held about 20 to 30 channels, which really wasn't enough for the town. So it wasn't enough for a town. So now the cellular system is the division of a city into small cells, hence cell phone, right? So this allows extensive frequency reuse across the city. So millions and millions of people can be talking at once. So what's the difference? How can this antenna still work when one's like so small, fits in your hand, in your pocket, where one's like a gigantic antenna, radio antenna? Well, these radio antennas are much larger because their waves are much larger. The radio waves are about 3 to 4 meters, where a cell phone antenna is really small and have much smaller wavelengths and work on a very small frequency.
About facts and terms about cellular antennas. To begin with, the largest component in a wireless gadget is the antenna. Many times, its footprint limits the size of mobile devices. So if you shrink the size of the antenna, we can shrink the mobile device. There are multiple antennas on each phone. Primary cellular antenna is the first one. This antenna is the primary communication antenna on the smartphone. This antenna typically is the only cellular antenna that transmits. The requirements for the transmitting portion of the primary cell antenna are the specific absorption rate and the total radiated power. Rate, all it does is measures the amount of energy absorbed by the human body when the phone is transmitting radio frequency energy. SAR is a function of the electrical conductivity induced E field from the radiated energy and the mass density of the tissue. The units of SAR are weight over kilogram or milli weight over grams. As you can see, the formula used to calculate SAR is given. Yeah. Now the total radiated power, it measures how much power is radiated by an antenna when the antenna is connected to an actual radio or transmitter. TRP is a function of not just the antenna but also the radio or transmitter and the connection between the radio and the antenna. The formula to calculate TRP is given below, where R is the region over which the integral is performed, and theta and phi are just the normal spherical coordinates. Diversity cellular antenna is the second antenna found in a cellular device. This antenna typically receives signals only. The diversity antenna's job is to try to provide an independent sample of data from the signals in the vicinity of the phone. The mobile phone's receiver will then choose the receive signal with the most energy or combine diversity in order to sum the powers from the two receiving cellular antennas. GPS and Wi-Fi antennas are on just about every cell phone these days. GPS antenna on smartphones are receive-only antennas. The bandwidth requirement is fairly small and they are located towards the top of the device. Wi-Fi antennas has the highest frequency on the mobile device and hence is the smallest antenna. Wi-Fi antennas are simultaneously used for transmit and receive. The Wi-Fi antenna is typically located on the top of the device with the GPS antenna. NFC antennas. NFC stands for Near Field Communications. NFC antennas operate at low frequency on small devices. A consequence of this is that the radiation efficiency of an NFC antenna will be about 0. Hence, an NFC antenna isn't an antenna at all. It is really just a big inductor. As you know, inductors can be made to couple together. That is, there exists mutual coupling. If the magnetic fields from one inductor pass near another inductor, an induced current will exist within the second inductor. This is contactless energy transfer, exactly what NFC requires. A good NFC antenna is as large as a wrapped coil of wire. Recall that a loop of wire around the material gives a strong magnetic field within the loop, so the more turns you have, the more inductance you create, which is better for the NFC antenna. This diagram on the slide illustrates NFC loop antennas interacting. So as you can see, as the two coils interact, there's an induced current in the smartphone's NFC antenna. This current can then be read and we have communication. Some applications of NFC include swipe proximity payments such as Google Wallet for paying at Starbucks, information exchange at small distances, for instance touching smartphones to share contact information, and simplified setup of devices such as Wi-Fi and Bluetooth. Some facts about cellular antennas. Is a tall antenna more powerful than a short antenna? No. It is a popular misconception that the bigger or taller the antenna, the more powerful or better it is. The length of antennas used in different types of communication is generally depicted by the frequency being used rather than the power of the antenna. Lower frequencies have longer wavelengths. Therefore, to achieve the same radiation pattern with the same energy, antenna length must be longer in low frequency communications than high frequency communications. These two antennas will achieve the same range in their respective frequencies under the same conditions, but their length difference is simply due to the frequency that each antenna is transmitting. Second fact, is a dual band antenna better than a single antenna? No. Ideally, a most efficient antenna should be tuned to one specific frequency. However, cellular communications use a wide frequency spectrum. This makes dual band antennas less efficient than single band antennas. However, dual band cellular antennas are still reasonably efficient. It is usually required that the antenna be as good a radiator as possible in both hands. Hence, dual band antennas are a necessity, but definitely not better. Now, a fun fact about cellular antennas. In 1913, the Eiffel Tower was used as an antenna. Back when communication was at very low frequency, the antennas had to be very large to get any sort of radiation. The Eiffel Tower fit this criteria well and was used to communicate with the United States Naval Observatory in Arlington, Virginia.
When we have 1G, 2G, 3G, 4G, we've heard of these terms before, different kind of technologies. With 1G, it works. It's the first generation of mobile networks. It runs on analog signals. It does mainly text and messaging. 2G, it runs more on narrowband digital networks, better quality. It reduces the complexity and can be used anywhere in the world. And then when we go on to 3G, and 3G is when we use your cell phones. You have 3G on your cell phones. You get internet. You get faster speeds. It builds on the same infrastructure of 2G, utilizes some different technologies. Then when we have 4G networks, that's like the new Bell subscription services if you have, and then you have faster data transmission rates. They have all those fancy commercials you see every now and then about 4G networks. Now, before we go into we got to put some kind of structure into what the different technologies are that transmit the information. Well, we have 3 different technologies that I want to focus on, and 2 primary technologies that I want to compare. One of the technologies I want to talk about is the FDMA, and that's called the Frequency Division Multiple Access Technology. And then we have Time Division Multiple Access Technology. Now, what is FDMA? FDMA is when you put each call on a separate frequency from a range from 824 megahertz to 893 megahertz. And each call will have its own separate frequency, and that is the frequency it will run on. And then we compare that with TDMA, which is Time Division Multiple Access. Time Division Multiple Access puts each cell on a certain portion of time, and you'll see that on the next slide. So in general terms, what is better, FDMA or TDMA? Well, we have TDMA that beats FDMA. The reason for that is TDMA compresses for less space, and it puts the call on 1/3 of the time per radio signal. It has 3 times the capacity of an FDMA technology. And another thing I would like to add, we have IS-54. It's a type of technology. It runs on an 800 megahertz range, whereas IS-136 runs on a 1900 megahertz range. But how does TDMA actually come into play? TDMA is used for 2G and in the form of GSM or CDMA. And what GSM is used for encryption. It makes the phone calls more secure. It operates in the frequency range listed below, around 1.9 gigahertz. I haven't talked much about CDMA. CDMA is a spread spectrum. We have data sent in small pieces over a number of frequencies available in a specific range. And companies that use this kind of technology could be like Verizon, Sprint, and they require no SIM card. And maybe you ever owned a phone that had this technology. 3G, it uses there's 3 different types of technologies that we researched upon for 3G. There's CDMA 2000, WCDMA, TDC, SCDMA. There's just a bunch of fancy names with different features for each of these technologies. And on the right, you'll see the graph of how the data traffic growth grew when 3G was introduced in 2008, 2009, 2010. How we had 3G device that was introduced, monthly pay. Then we had the iPhone that came out that skyrocketed 3G technologies. Then you have the Palm Pre was also a great success. Then you have now recently you have the iPhone 4 and iPhone 5, and now these run on the 4G network. The 4G network is a structure of HSPA. It's similar structure to 3G, and it builds on the YCDMA, wideband code division multiple access frequency.
Here we're talking about a dipole antenna. So what a dipole antenna is, as we explained before, it's a simplest type of antenna. Now it consists of two conductive wire rods. They're bilaterally symmetrical, and as you can see in this picture, one of the rod goes up, one of them points down. And this more common type of antenna is half wave dipole antenna, and its length is half of the wavelength that it generates, as you can see. So for example, in the picture on the bottom, the wavelength, the total length of the two rods would be half of the wavelength that it generates. Now how it works is that, again, the current flows through all the wires, and the electromagnetic waves are both in phase, so they add up and they cause a radiation. Now, the efficiency and bandwidth. Now, the bandwidth in the antennas are expressed basically in terms of percent of bandwidth, and how you can actually make it more efficient and sort of amplify the bandwidth is you simply have thicker material. So, for example, if you have a thin antenna, if you somehow have it made of a thicker material or fatter material, it will cause your bandwidth to be much larger. Now, the efficiency in the antenna simply relies mainly on the impedance matching. Now, this is an important process because what it is basically you're removing the mismatch loss, and what that is minimizing the reflection coefficient, as my colleague was talking about, and maximizing the power delivered. Now, how you do this is basically your antenna is a load, basically, right? So you want the load or antenna impedance to match the transmission line. Now, many types of antennas actually do come with their own impedance matching circuitry to allow the antenna's impedance match the impedance of the transmission line. As you can see, these are the picture. The picture on the left is basically the circuitry and the antenna. Now, that's the input reflection coefficient that we're talking about, and we want that to match the load's impedance, which is the antenna. And picture on the right is just a method that they chose. This method is used to do impedance matching. Now, here we're talking about the design of antennas and cellular devices. There are multiple antennas used in the design of cell phone carriers, and each phone, basically, as we talked about before, has its own carrier requirements, and above that there's also regulations that the government has on these devices, such as SAR, which is basically how much radiation is allowed to be exposed to a human body, right? So they have kind of control on that. But other than that, there are many types of antennas used in a cell phone, like specifically smartphone. And the most important one is a primary cellular antenna, which is basically responsible for transmitting and receiving electromagnetic waves. And the second one is a diversity cellular antenna for receiving only, GPS antenna to connect to the satellite, and also a Wi-Fi antenna. There is also another sort of antenna that's it's only used for connecting with other cell phones in a close range, which some phones have and some phones don't. Now, the primary cellular antenna has a low band and a high band, right? So it operates but majority of cell phone devices actually cover many bands of frequencies, so the combination of them. And as you can see in this picture, the antenna, the primary cellular antenna, is actually covering a lot of the surface behind the phone, and that is done on purpose to actually make the antenna more efficient. And it's basically a similar design with a dipole antenna, but as you can see, the center is kind of move towards one side.
The location of antennas, and in this slide I'll talk about the evolution of the antennas. So one of the first phone was the Motorola MicroTac, which came out in 1989. It used an external antenna, and it was a whip monopole. This yielded really good results, especially compared to the later stubby antennas. The later one, as you can see, the middle phone, is the Nokia 5110, which came out in 1998. This uses stubby antenna. Although this was not as efficient as the whip monopole, it was still allowed, made feasible through the advancements of cellular network. Because of the higher number of cellular towers at that time, we could use the stubby antennas and yielded good results. Later, after a year later, the Nokia 3210 came out, which was a huge success. It sold over 160 million sets during its lifetime, and it used internal antennas. So this revolutionized the location of the antenna in terms of where to go. The problem with this was that it was prone to blocking of signal by your hand or the case if you used it. But the advantage of this was that it had little chance of abuse by users. People like to play with the stubby antenna, or they used to whip the whip monopole around, and it always messed it up. Location of antenna now. Nowadays, most of the phones you find have an antenna at the bottom of the phone internally. This is shown in the diagram right there, circled in red. That's the antenna. That's where the signal is inputted and it radiates. The main reason for putting the antenna at the bottom is that it reduces SAR. SAR, as previously mentioned, is the specific absorption rate, which measures the amount of energy absorbed by the human body when the phone is transmitting. So the reason for putting it at the bottom is that it increases the distance between the antenna and your skull, which that's the main worry that scientists have, that they want to keep it away from the skull and the brain, where it might damage the brain. The antenna is ACC1, which has a really innovative antenna design. It utilizes a metallic back as an antenna. As you can see, the break in the antenna, which is the non-metallic part on the ACC1 back, it allows the antenna to radiate the signal. This is tricky to do because of the parasitic capacitance of the whole aluminum back. However, ACC1 managed to do this, which makes it a great antenna design.
We'll be covering an inverted F antenna, which is simply just a dipole antenna, as you see on your left hand side, and the bottom half is just expanded out and the top is just bent into an L shape. It is called an inverted F antenna because it looks like an inverted F. Simply with this antenna there is a capacitance impedance, and which can be equated by putting a parallel inductance and to match it up. The specialty about this antenna is that it supports both radiation and impedance. A typical F antenna is used in iPhone 4S and also several other devices. So here we have this a inverted F antenna simulation on MATLAB using OpenEMS. As you can see, the ground plate is a really large plate in the bottom half, and we have what is an inverted F on the top half, which creates the radiation. We also have a zoomed in version on the right hand side, as you can see. These are the results that we got from our simulation on MATLAB and using OpenEMS. Here is our feed point impedance and our reflection coefficient with our frequency. So this F antenna was optimized for the frequency of 2.42 gigahertz, as you can see from the reflection coefficient. And as typical with dipole antennas and slot antennas, it has an approximate 7% bandwidth. Also, as you can see, according to frequency, your impedance is at the required approximately 50 ohms. Also, our electric field at volts per meter at our 2.42 gigahertz frequency. As you can see from this, it is spreading in a radial direction.